And now for one of our favorite things to do, Calculus 3, multivariable calculus, also known as Math 2650 locally. Third exam from fall 2024. Now this is the really fun stuff where we're getting into integration that really test us to say, hey, are we able to describe things geometrically? That will be the make or break for this exam. All right, well, we got 6 multiple choice problems, 4 workout problems, a lot of fun ahead. But before we get to the fun stuff, we always got to make sure we start by putting our name. Because if we don't put our name, we won't get the credit. All right, well, let's have some fun. And here we go. Number 1. Find the volume of the region lying below the surface, z equals f of x, y equals 12 minus 4x minus 2y, and above the rectangle, x goes 0 to 1, y goes 0 to 3. Now, we can try to argue this geometrically, but look, it's volume. And how do you find volume? Well, volume is you integrate over your region, your height. You say, okay, well, great. That certainly does it. And what's our region? It's a nice square. So you say, all right, let's just go ahead and do it. So we're going to integrate. Our height is from the xy plane up to the surface. And so it's just the function, 12 minus 4x minus 2y. And you can choose the order of integration. I'll just say dy dx. X goes 0, 1. Y goes 0, 3. And so we're just going to work it out. Not the most exciting way to solve it, but it works, right? We're not going to get like bonus points for style. We get points for correct answers. And so get the answer, right? That's your job. And we want to do our job really well. All right, so we're integrating with respect to y. That means we're treating our x's like a constant. So what do we have? Well, we have 12x. Sorry, 12y. I can't believe I messed that up, right? Integrating with respect to y. 12y minus 4xy minus y squared. Okay, evaluate 0 to 3 dx. Now, plug in 0, 0, 0, 0. Great news. Plug in 3. What do we have? Well, we're going to get integral 0 to 1, 36 minus 12x minus 9. And we could have said, oh, just to help us, y equals 0 to y equals 3. And dx, well, this is the integral 36 minus 9. That's 25. That's not 25. Oh my gosh, 27. Yeah, check yourself before you wreck yourself, right? Like the great philosophers of mathematics would say. All right, so this is 27x, and the integral of 12x will be 6x squared. Evaluate 0 to 1, which gives us 27 minus 6, or 21. And that's an option. And there we go. Okay, not the most interesting, but that's okay. We do need practice with integration because, well, that's what most of this test is about. Number 2. So, we're given a double integral, and 0 to 4, x over 2 to root x, dy dx. And we're asked, hey, this is equal to one of these. Now notice, all of these have dx dy. So what is that? Well, this is saying we're going to change order of integration. This is a classic problem. If there's anything that we can predict that's going to be on this test, this we can predict. There's going to be some place where we change order of integration. Now, how do we do it? Well, for me, the easiest way is to say, let's get a picture. And so we say, currently, the bounds are describing a region. So we have x goes 0 to 4. Right, that's our outer layer. Our inner layer says y goes from x over 2 up to square root of x. And so we draw a quick picture here. We have square root of x. So there's square root of x. We have 1/2 x. And, well, we're suspicious. Where do we think they intersect? I'm going to guess 4. Let's check. 4 divided by 2 is 2. Square root of 4 is 2. So it's like, okay, so this is 4, and y equals 2. And now the other point of intersection is at 0, 0. And so I say, aha, great. Now we have our region. I'm going to do a quick bit of shading here. So from 0 to 4, we go from x over 2 up to square root of x. And so in particular, we are slicing currently this way. Now, changing order of integration says we're going to change the way we slice. So now we're going to slice perpendicular. We're going to slice that way. Well, okay. What can we say? Well, we're going to do our new integral. Integral. The function doesn't change because that doesn't depend on the order of integration. And now we have our dx dy. And we say, okay, well, where does y go from? Well, the lowest value of y is 0. Highest is 2. 0 to 2. Well, let's see. That knocks out A and B and C. Oh, we could have knocked out C right from the very beginning. C was nonsense, right? That just changed the order. You can't have functions on the outer layer. The outer layer is always number to number. The next layer in, function to function, curve to curve, if we were doing triple integrals, it's surface to surface. You can't have a function on the outer layer. Okay, so now it's a coin flip, right? No, because we're going to actually go one step further. We have that these are the curves. This is y equals root x, and y equals x over 2. Well, if you solve for x, you get x equals y squared, and here you get x equals 2y. And we say we want to go from low to high, left to right. So we're going to go from y squared up to 2y. So we want y squared to 2y, low value to high value. So our answer is E. And be careful here, right? They're so close to each other. So this is always, we go from small to big. So, bottom up to top, left up to right. All right, there we go. And great, we're doing wonderful. Let's keep it up. Our third problem. Let R be the region in the lower half plane, y less than or equal to 0, between the circles x squared plus y squared equals 4 and x squared plus y squared equals 25. Change the double integral over r 2x squared dA, from rectangular coordinates to polar coordinates. Okay, well, we have a couple of facts we should know. X is r cosine theta, y is r sine theta, and the other thing we should note is dA is r d theta. So let's update this portion. So we would have 2 times the x, r cosine theta quantity squared, times r d theta. Okay, and we have our bounds. So in particular, this should be 2 r squared times r makes an r cubed cosine squared theta. Let's check in to see if we know what these are. That says r squared. Nope, we want r cubed. That says r squared. Nope. That says r squared. Nope. That says r cubed cosine squared, so that's still in the running. That says r cubed sine squared. Oh, we haven't even done the bounds, and we're already done. Oh my gosh. What? Well, that can happen. It's not about finishing the whole problem. It's about doing enough to know which one's right. But let's go ahead and check the bounds, just for sanity's sake. So x squared plus y squared equals 4. That's a circle of radius 2. X squared plus y squared equals 25 is a circle of radius 5. And we want to be in between, but also downstairs. So we're down here. So we say, okay, where does theta go from? Well, we start at pi, and we go to 2 pi. So theta would be pi to 2 pi, which is what it says. And now, if you fix the theta, you say, well, what happens to r? Well, we come out from the center. We start at 2. We go till we hit 5. So the bound should be 2 to 5. And yeah, it really does check all our boxes. But, you know, as I said, do enough to get the right answer and you're great. Because that's one of the great things about multiple choice. We can take advantage of it being multiple choice. All right, number 4. Let S be the solid in the first octant. Sort of like first quadrant, where x and y are positive. First octant says all your variables, x, y, z, are all positive. And we're bounded by the surfaces x equals 0, z equals 0, y equals z, y equals 1, and x equals y squared. Whew! Oh my goodness. Well, they gave us a picture here. All right, so here's our picture. The integral over this solid with integration over dx, dz, dy is given by which of the following? All right, so how do we set this up? Now, there's a couple ways to do this, and let's start by reasoning through the dx part. So dx part says we are running parallel to the x direction. Now, which surfaces are we going in between? So as I'm coming here, which surfaces do I hit? The back side is this surface back here. That's our x equals 0 surface. Okay, now the front side, it's this curved surface. Now where is this surface coming from? Well, if you look, this is the surface x equals y squared. It goes straight up and down. All right, so what does that tell us? Well, it tells us that our inner layer, when we're setting up our layers here for our function x, y, z, dx, dy, dz, the x needs to go from the back to the front, 0 to y squared. So what has 0 to y squared? Well, okay, A, still in the running. 0 to z, nope. C, still in the running. 0 to z, nope. Y squared to 1, nope. So we now narrowed it down. Okay, so now that we know where that surface is going, how do we do our next one? Well, here is what I like to do. I say, look, I've already handled x. So I'm going to imagine that I have x, and I'm going to just tilt till I'm looking straight down the axis. And ask the question, what do I see? So it's like, you can, if you don't like to think of tilting, it's like move so you can look straight down that axis. If we do that, we're going to see just y and z. So in yz, because our x-axis is that point, right? It's like at the origin, we see this shape. And, well, how far do we go? Well, we go up to y equals 1. And then there's this other surface here, y equals z. Okay, now, let's talk y. Where does y go from? Well, if I'm looking at this, and I say, well, y is going to go, let's see. Oh, yeah, I have to be careful here. We're going dz. I wasn't paying attention. My apologies. We're in the dy dz plane. Where does z go between? Well, z is going to go up and down, right? We got to go in the z direction. And where do we go? Well, we go from z equals 0 up to z equals y. Okay, so our next layer needs to be 0 to y. Okay, that rules A out. And now we're done. Now you might say, okay, well wait, what about y? Well, we can actually see it. Where does y go from? It goes from 0 to 1. Okay, so how do you do these? I think that setting up and understanding bounds in 3 dimensions, it is super challenging. I'm not going to joke around about that. It's serious. But how do we do it? Think about, okay, what surfaces are we going in between? And if you want your innermost layer, okay, in the x direction, you're going back and forth this direction. If we had been y on the innermost layer, we would go in that direction. If it had been z, we'd be going up and down. So once we understand, oh, I'm going back and forth, you say, okay, what's on the back side? Identify that surface. Move forward. What's on the front side? Identify that surface. And that gives us our bounds. Move into one lower dimension. Now we have a 2-dimensional problem and work on that. And so it's just a matter of just slowly work your way through it. You can do it. You can do this. This does take practice. That's why we're here. Because if we practice, we're going to be great, and we'll do a great job on the real test. That's right. We're going to be marvelous. All right. Let's keep moving. Number 5. Find div. Now, div is short for divergence. And, okay, find the divergence of f. And we have f is this vector-valued function. Now, if you see a problem, then you say, I hope I see a divergence problem, because divergence is the fun one. And why do I say that? Well, divergence of f, the way you find that is if you think of this as the divergence of a vector-valued function, m n p. That is your m sub x plus n sub y plus p sub z. So it's going to result in a single function, and so there shouldn't be any vectors. And notice there's no vectors here, so that's good. And you just go through and say, okay, go to the first slot and say, take the derivative of that with respect to x. All right, well, the derivative of 2x to the 3 halves with respect to x, the 3 halves comes down. 2 times 3 halves is 3, x to the 1 half. And this doesn't really matter because there's no x. Okay, so we should have something with 3x to the 1 half. Okay, so they all have that. All right, no worries. Now we go to the second slot. And we say, okay, second slot, that's our n. Take the derivative with respect to y. There's no y there, so that doesn't need to worry about it. What's the derivative of 7xyz with respect to y? 7xz. Okay, so we need something with the 7xz. Okay, that has 7xz. That has 7xz. That has 7xz. So now it's possible it might cancel later, but we are suspicious enough. We'll cross those two off for now. Okay, now the last slot. We're almost done with this one. See, divergence problems are fun. Okay, we're taking the derivative with respect to z. That doesn't have any z. And we're like, okay, derivative e to the z with respect to z is e to the z. Okay, so we should have an e to the z. All right, now these terms all have e to the z, but that's all it should have. No, too much extra. Way too much extra. And this is just right. All right, and there we go. So divergence is just beautiful. You're just taking your partial derivatives and adding them up. It's the fun one. Curl, that's a different problem. It's not the problem we're doing. And so that one you have to work on. But you should cross your fingers and like, please give us divergence. Please give us divergence. Good times. Okay, number 6. Set up a double integral to find the flux of the vector-valued function yi plus xj plus zk, and for the surface with upward-pointing normals given by the portion of z equals 25 minus x squared minus y squared with z greater than or equal to 0. Let R represent the region x squared plus y squared less than or equal to 25 in the xy plane. All right, so our f, if we write it in a slightly different notation, This is our y, x, z. And normally we write this as m, n, p. Okay. So m is y, n is x, p is z. So the picture here, we don't need to actually know this picture to do the problem, but if we were going to do this, it turns out that what you have is an upside down bowl. So you have this shape here, and what we have is there's this region, and the region is this part here. So we have this upside down bowl, and we're trying to find the flux. Now, as a reminder, flux means flow. So how does one find the flow? Well, what you'd like is you take the normal vector to the surface, and you dot it with f, and then you integrate over that surface. Well, things get messy when you start doing normal vectors and all these other things. But here's the really cool thing. It turns out that you get two messy things, and the two messy things cancel. So, in particular, if you have a flow through a surface, then what you say is, lo and behold, it becomes the integral over your region of minus m fx minus n fy plus p. Now, where are all these things coming from? You're taking your m and p, that's your flow, and you're dotting it with minus fx minus fy and 1. This right here, this is perpendicular to the surface. So it's acting like the normal. The only thing that's at issue here is it's not a proper normal vector because it doesn't have the right magnitude. But that's where the dA comes into play. And so you get that little sort of cancellation going out here. So the flux of your flow, the flow of your vector field. So this is your vector field dot your normal. Now, what is everything? Well, let's go through and write it down. Now, f is our surface. So here, f of xy, that's 25 minus x squared minus y squared. So we have, and we'll put it here, integral over our region minus m, so that's minus y, times f sub x, that's minus 2x, minus n, so that's minus x, times f sub y, that's minus 2y, and then plus p, plus z. Now, cool. That is almost it, but not quite. There's one subtle thing. This is a region in the plane. So our integral needs to be x and y. There's a z there. That's not going to fly. So you have to replace the z. And how do you do it? Well, we use the fact that we can know z equals f of xy. So we still have these other pieces here. So there's a 2xy, and so that's going to give us integral of our region 4xy, and then plus our z, so 25 minus x squared minus y squared. Okay, so this is what we're looking for, a 4xy plus 25 minus x squared minus y squared. And I can see it here, c, 4xy plus 25 minus x squared minus y squared. And all right, that was our last multiple choice one. So yeah, know your flux through your surface. It turns out to be really nice, really elegant, if you remember the formula. But of course, we have ways to remember formulas, don't we? Practice, practice. Okay, that brings us into our workout. Okay, long answer problems. Well, hopefully not too long. We still have time, but we don't want to take too much time. We want to save some time to review, right? Yeah. Number 7. Consider the solid cone lying above z equals root x squared plus y squared and below z equals 1. Assume that the density of the mass of the solid is given by delta xyz equals 20z. So the picture here, z equals x squared plus y squared, is a cone going like this, and we're going up to the top. So we have z equals 1 on the top, and then we have our z equals square root of x squared plus y squared on the side. Now, our density varies with z, which means at the bottom, almost no density, right? Because z is very small. But then as you move up, you start getting denser. And so it gets very dense at the top, but not very dense at the bottom. So, okay, so that's sort of our idea. Now, we need to get some handle on this. Now, to do this, we're going to, well, let's start by setting up our integral. What's the mass? Right, let's do that. What does this become? So mass, whether you're working 1, 2, or 3 dimensions, it's always the same. You're integrating. In this case, we're 3 dimensions. You're integrating over your solid, your density. So that's your mass. Okay, so for us, we have to find a way to integrate this. So we say, okay, what makes sense? Looking at our shape, we say, you know, this shape is very beautiful. In particular, has that nice rotational symmetry. So it's rotationally symmetric. If you spin it around the z-axis, it looks the same. Well, what kind of things work well when you have that rotational symmetry? Or what's the best way to describe that? And the answer is cylindrical coordinates. So cylindrical coordinates works great for anything with rotational symmetry. So what we'll do is we're going to take this and we're going to slice. So imagine just coming down and slicing. And I call it the RZ plane. So we're going to, here's our z-axis. And here we'll have the r-axis. And when you slice this cone, what you're going to get is a triangle. And we know it has a height 1. And we see z equals square root of x squared plus y squared. Well, that's like z equals r. And we say, okay, so that's the description here in the RZ plane. So we're ready to talk about how to set things up. So in cylindrical coordinates, some nice basic facts. We have our z, r, and theta, and dv is r, dz, dr, d theta. So our mass formula is going to become the following. We're integrating, and we'll set our bounds in a second. Our density, 20z. Well, that's in terms of x, y, z. We need in terms of z, r, theta. So what is it actually? It's 20z, right? Because z is still z. The z in Cartesian coordinates matches the z in cylindrical coordinates. So 20z. And now dz, we have r, dz, dr, d theta. Theta, because it's rotationally symmetric, it's going to be 0 to 2 pi, all the way around. R, well, if we look here, R, we have this point. We know it hits at z equals 1 and z equals r, so r goes 0 to 1. How about z? Well, what happens if I just pick a random z value, random r value, I should say, z goes between those two. So I go from z equals r to z equals 1. Okay, well, we're going to be a little bit short of space, so that's okay. No worries. We'll just patiently work through this one layer at a time. So let's start on the inner layer. Integrate with respect to z. Well, the integral of 20z is 10z squared. So integral 0 to 2 pi, integral 0 to 1, 10z squared r, and then we're going to evaluate z equals r to z equals 1, and d r d theta. So that becomes integral 0 to 2 pi and integral 0 to 1, and plug that in. We'll get 10z squared, and, 10r, because z equals 1, not r, 10r. So 10r, subtract, now plug in z equals r, 10r squared times r, so that's 10r cubed, dr d theta. All right. We're going to run out of space here. Well, okay, so that becomes integral 0 to 2 pi. We'll hopefully have some space. We'll work it all out. Don't worry. Integral 0 to 2 pi. And what do we have? Well, integrating with respect to r. That's 5r squared, right? Because you add 1, divide by 5. And then minus, here, add 1, that's 4, and divide. And so that's 5 halves r to the 4th. And evaluate r equals 0, r equals 1, d theta. Well, we plug in 0, we get 0. Good. Plug in 1, 5 minus 5 halves. So this becomes integral 0 to 2 pi of 5 halves. Well, okay, that's 5 halves theta from 0 to 2 pi. And plug in 0 to get 0. 5 halves times 2 pi is 5 pi. Okay, so, all right. That's the answer for part A. The mass of the solid is 5 pi. All right. Now, let's go on to part B. Okay, find the z-coordinate of the center of mass. Now, how do we find the z-coordinate? Well, that sometimes is denoted z bar, sort of like, the average, if you will, the weighted average. And this is the ratio of what? Of the moment with respect to the xy plane divided by mass. Now, we already know the mass is 5 pi. So you say, okay, so it's something over 5 pi. All right, so that's our z bar, is something over 5 pi. Now, okay, that can't be the answer, right? You got to know the something. Well, okay, so we got to find the moment. Now, how do you find moment? Well, moment is a combination of two things. It's going to be the same integral. We still have density. That doesn't change. But now you add one more thing. And I call it distance. Okay, so density and distance. So what is the distance? Well, it's the distance to the xy plane. And what is the distance to the xy plane? This density, I can say the right words at the right time. Density is 20z. Distance is z. All right, that's how far you are to the xy plane. Okay, so we're going to set up. We'll just copy it, right? Recycle. And so, because the bounds are the same, so don't need to change that. And now, the only thing that happens is there's an extra factor of z. So 20z squared, r dz dr d theta. Well, okay, again, one layer at a time. We start with integrating with respect to z. Add 1, divide by that power. So this will become 0 to 2 pi, 0 to 1, and now 20 over 3 z cubed times r, and evaluate that from z equals r to z equals 1. And then we have our dr d theta. Okay, so that is integral 0 to 2 pi, and integral 0 to 1, we're still evaluating. Plug in z equals 1. 20 over 3 times r. Plug in z equals r. Well, we have an r cubed and an r. And so that's r to the 4th. So minus 20 over 3 r to the 4th. Okay, and dr d theta. Well, now we integrate that. And what do we have? Integral 0 to 2 pi. And here, add 1, divide. So add 1 will give us a 2, divide by 2. So that's 10 thirds, r squared. Okay, add 1, that gives us r to the 5th, divide by 5. That's 4 thirds, r to the 5th. Okay, and evaluate r equals 0 to r equals 1. And, oh, I couldn't quite fit it in, but there's a d theta there. Okay, now we plug in. Plug in 0, get 0. Plug in 1. Well, you get 10 over 3 minus 4 over 3. That's 6 over 3. And now we're in the home stretch, right? Because 6 over 3 is what? It's 2. And the integral of 2 is 2 theta. Evaluate from 0 to 2 pi, which gives us 4 pi. Oh, okay, so our moment is 4 pi. That goes here. So we have 4 pi over 5 pi, meaning our z-coordinate is 4/5. Whew. Okay, now that was a workout. Let's pause for a second and ask a question. Is it reasonable? Well, let's look at our shape. Our shape goes from 0 to 1. It's bigger at the top, and it's not just bigger at the top, it's denser at the top. So we should have our center of mass should be near the top, but it shouldn't be above 1, because that would be crazy. So it should be a number a little below 1, but not too far. And 4/5, 0.8, that fits the bill. So it's at least in the ballpark. All right, now, we found z bar. That was the hard part. We should put a box here. We deserve to box it. So we have z bar. Find the center of mass. Well, we've already found one piece. How do you find the other two? Well, let's not work hard. What's going to happen is we say, hey, center of mass respects symmetry. So we have our aha moment. So by symmetry, what's true? Well, what we can say is, looking at this shape, because we're rotationally symmetric around the z-axis, the center of mass is on the z-axis. Well, what does that give us? It tells us the following. So x bar and y bar are both 0. We already found z bar, so our answer is 0, 0, and 4/5. Now, a clue that this should be a very straightforward part of the problem, it's only worth 1 point. And the reason it's 1 point is like, oh, you have symmetry. So if you see something only worth 1 or 2 points, there's got to be like a quick, easy way to do it. They give points to the steps which are hard. And there was definitely a lot of things that had to be done in this one. Oh my gosh. When they say this is a workout problem, I didn't think they meant it literally. But good news, I think this might be as bad as it gets. Okay, so maybe it's not as... No, come on. It's not that bad. And before we start this problem, I got to tell you, this is my problem. I wrote this. And I really hope we do well. I hope we enjoy it. I'm sure we'll do great. Let R be the region in the xy plane bounded by the parabolas y equals minus x squared minus 2x, y equals minus x squared plus 2x, and y equals minus x squared plus 4. And so there's three parabolas, right? There's like this big one, these two small ones. Of course, what does that mean by big and small? We have this region. All right. Use the change of variables u equals x and v equals y plus x squared to find that integral. All right. Now, so this is a change of variable problem, and sometimes change of variables problems are sometimes called the Jacobian type problems, and that's because Jacobians come into play. So we need to spend some time talking about what's going on here. What do we need to do? So let's remind ourselves, every integral has three parts. What are they? Well, there's the function, there's the bounds, and those are the ones that most people think of. But then there's the how we split things up. And that actually is really important. And that's where we should start our conversation. And so this part right here, this is in some sense the dA. So currently, as stated, this dA looks like dx dy or dy dx. That's what we currently have. We're going to switch to new variables, and we're going to u and v. So the question is, how does dx dy and dy dx relate to du, dv, and dv, du? And so, to answer that question, we're going to use the Jacobian. So how does the Jacobian work? Well, we have our relationships. And the good thing is, they're going to give us these relationships. We're not going to have to sort of pull them out of air, because if we did, oh my gosh, ooh, that's tough. But when they're given to us, we say, beautiful. And what we do is we're going to set up a 2x2 determinant. And okay, so we have our u and v. Now, I'll tell you, sometimes I don't get this exactly right, but you don't have to worry. You see, the Jacobian forgives all. As long as you just say, you're looking at all the partial derivatives. So what's the partial derivatives of u with respect to x and y? What's the partial derivatives of v with respect to x and y? Put them in some reasonable order, and we're going to take the determinant, and then we're going to take the absolute value of the determinant. This is what we call the Jacobian. And that's going to tell us how things relate. And in particular, what we're going to find out is that du dv is equal to the Jacobian of this dx dy. All right. Well, let's do this computation. So we have a 2x2 matrix. Let's fill it up. U sub x is 1. U sub y is 0. V sub x is 2x. And v sub y is 1. And so take this 2x2 determinant. What do we get? We get 1 minus 0 is 1. And so, good news for us. Du dv is dx dy. All right, that's going to make things a little bit easier to work with. So that handles that portion. And I always like to start with doing that portion because it can affect the function. Now let's get into the function part. So our function, since we don't have to worry about anything being part of our updating how we split things up, is we say, well, we currently have 2e to the y plus x squared squared. All right, great. Now, what do we need? Well, we need to somehow rewrite this in terms that we can use in terms of u and v. So we say, well, look for u and v. And we say, well, wait a second, y plus x squared, that looks like the y plus x squared. It's exactly it. So this is going to become 2e to the v squared. So now we can rewrite our function, this piece. We figured out how to rewrite it in terms of our new variables. That says our function is done. Well, that was very quick. Okay. Well, now we have the bounds. Okay, so let's talk about our bounds. Now, the thing is, the way we get our new bounds is we start with our old bounds. And we say, well, what are our bounding curves? We have 3 bounding curves. So let's write them down. Bounding curves. They are, and we don't even have to think. They're given to us. So y equals minus x squared minus 2x. Y equals minus x squared plus 2x. Y equals minus x squared plus 4. And as a reminder, we have in the back of our minds u equals x, v equals y plus x squared. So what we want to do is we want to use these to take these equations and replace each equation in terms of u and v. Now, because I see these minus x squareds, I really want them to be y plus x squareds. So let's add x squared to both sides. Y plus x squared equals minus 2x. Y plus x squared equals plus 2x. Y plus x squared equals 4. And now the y plus x squared becomes v. Now what do we do with the x? Well, x is u. So v equals minus 2u. V equals plus 2u. V equals 4. So this, we have 3 new bounding curves. This bounds in the UV plane. Okay, so in essence, we're done. But let's clean it up. Okay, because I want to understand the shape here. So I'm in the UV plane. We have 3 pieces. We have v equals 2u, which is a line that goes up. So that's v equals 2u. V equals minus 2u, which comes down. And we have v equals 4. So we have a triangle. So there's our triangle. All right. Well, we're ready to put it all together. So we had, this is almost off the top of the screen now. Let me pull it back down. And we're going to put all these pieces together. So we have our original integral here over our region 2e to the y plus x squared squared. Okay, it becomes integral of the function will be 2e to the v squared. And I forgot to write down dA. I'm going to write down dA. And now we have to make a choice. Do we do du dv or dv du? And you might say, do we have to make a choice? Well, we do, because it's not just a matter of rewriting. If all we had to do was rewrite, we wouldn't have to think. We have to find, which means that we're going to do an integral. So, question, do you want to integrate this with respect to v or with respect to u? We don't want to integrate with respect to v. E to the v squared, that's terrible. That's going to be a terrible integral. So we're not going to want to integrate with respect to v first. So we say, okay, let's integrate du dv. Because with respect to u is pretty straightforward because there's no u, so that won't be very hard. All right, let's start with the outer layer. Where does v go from? Well, v goes from the bottom part of the triangle up to the top part of the triangle. 0 to 4. Where does u go from? Well, now we're going in between. So on the right-hand side, we're at u equals 1/2 v. On the left-hand side, we're at u equals minus 1/2 v. So we're going to go from minus 1/2 v up to positive 1/2 v. And now we're ready. Everything is set. We've transformed our integral, and we can at least make progress. The original integral, hopeless. Hopeless. We'd never be able to make progress. But here, we can at least now do one layer. So we do our layer. When we integrate with respect to u, 2e to the v squared is a constant, so we have integral 0 to 4, 2e to the v, 2e to the v squared, got to put it upstairs, times u, evaluate from minus 1/2 v to positive 1/2 v, and this is u equals and u equals dv. So 1/2 v subtract minus 1/2 v tells us that this piece here, this part right here, all becomes v. So what do we have now? Well, this says that we have the integral 0 to 4, 2v e to the v squared dv. All right. Oh, now this, it's much better. Well, this is almost one you can do in your head, but just in case, we'll make a substitution. We've already used u and v, so we'll work our way through the alphabet. If you let w equal v squared, then dw becomes 2v dv. And so what we have here is that this is the integral of e to the w dw. But what are the bounds? Well, when you plug in 0, you get 0 squared is 0, and plug in 4, 4 squared is 16. So this is e to the w, evaluate from 0 to 16, which is e to the 16, subtract e to the 0, e to the 0 is 1. And there we go. So our answer is e to the 16 minus 1. Whew. Okay. Oh my gosh, there is a lot to do on this problem. So let's catch our breath and do a review, right? What actually happened? So when we have change of variables, we have to go through and say we need to update 3 pieces. How we break things up, our function, our bounds. Now, you kind of can jump around, but I always encourage you to start with the Jacobian piece of it. So you set up your 2 by 2 determinant, take your determinant, and that gives you a relationship between your du, dv, and your dx, dy. Once you have that, if you're really in a good shape where you don't have to worry, then everything else is pretty quick. Sometimes you have to say, oh, I have a little piece here attached to dx, dy, and you just grab that off of what you need. The function, say, look, how can I rewrite my old function in terms of the new variables? So look for the things that you're substituting. You're looking for x's and y plus x squared. And the same thing happens with your bounding curves. You figure out which curves actually bound your region. For each one, replace it in terms of v and u. And now you have your new region. And secretly, this problem actually was a little bit subtle because when you set it up, you had to make a choice, and you had to make the right choice. du dv versus dv du is very different here. And so think about which order you want to do things. What would you like to integrate with respect to first? That tells you the order of integration. But now, with all that work done, it becomes a very straightforward grind through and do your layers of integration. I know that there's a lot of small pieces here, and sometimes when you look at it all together, it can be very like, it can feel overwhelming, but I want to assure you, you don't need to be overwhelmed. You can just be merely whelmed, right? Break problems into the small parts, work on each part, and then know how to put it back together. That's how you solve problems. You are a problem solver. That's why you're here. You are becoming a fantastic problem solver. You can do this. You can do it. Practice, practice, practice. You'll become great at it. All right, come on. We got to keep going. We don't have all day, and we still have 2 problems left to work on. Okay, so number 9. So we're given a function. It's a vector-valued function. And show that f is conservative by finding a potential function. Now, what does it mean to say it's a potential function? In essence, the way I like to think of it says, oh, f, this capital F, it's a derivative of something. And so we say, oh, okay. So we're asking for the antiderivative. And so in particular, if it is conservative, what it says is that the first slot is the partial derivative with respect to x. The second slot is the partial derivative with respect to y. And the third slot is the derivative with respect to z. So, in other words, I have handed you a bunch of partial derivatives. I want you to tell me what was the function it came from. That's our goal. So we say, okay, well, if I know what the derivative with respect to x is, if I want to get my function, I integrate with respect to x. So we say, okay, so our function should be the integral of the first slot, y sine z with respect to x. Well, there's no x's in there, so that's a pretty straightforward integral. That's xy sine z. And you're like, well, that was really quick. Well, except you have to be careful because we integrate with respect to x, so there's a constant, and it's not a constant number, it's a constant of anything that doesn't have x involved. So it's a constant function. So anything which only has y's and z's is a constant with respect to x. But we say, you know what, we can play this game again. So now, instead of using the first slot, we go to the second slot. And make sure we underline the full second slot. We say, all right, that's cosine y plus x sine z dy. So integrating with respect to y, x and z's are like constants. Well, the integral of cosine is positive sine. That one is kind of tricky. I got to be honest with you. I always have to pause and like, is it? Is it? It is. It is. X sine z, well, there's no y, so that's like a constant, so the integral of that will be xy sine z. And now, plus some constant function with respect to y, so something which depends on x and z. Okay, well, third time. And we say, okay, hey, our function really could also have been found by taking the third slot and integrating with respect to z. All right, integral of 3z squared, z cubed with respect to z. Integral of cosine z is sine, and xy is a constant, so we get xy sine z. Plus, again, something which depends only on x and y. Okay, so now we can say, hey, we kind of have an idea of what our function looks like. We can stitch it together. The thing you need to check, what you need to check, is consistency if you have terms with multiple variables. So notice x, y, sine z, that has all 3 variables involved. So we say, is it consistent? Well, each one of these has an x, y, sine z. So if I have all 3 variables, has to show up all 3 times. If it had 2 of the variables, it would have to show up in the 2 variables that it was with. Maybe it was x and y, or x and z, or y and z. And if there's only 1 variable, it only has to show up in that part. Okay, so the xy sine z says, our final answer has to have an xy sine z. Okay, so that's part of it. what else do we have? Well, there's no pieces which have two variables, but we do have pieces with one variable, and pieces with one variable, those will always be there. So we have a sine y. Great. So that's going to be in there. We say, all right, so we have sine of y, and we'll throw that in, sine y. And we also have what? We have a z cubed. Say, okay, z cubed. And that will also be in there. Doesn't really matter the order that you put things in. And so there's our z cubed. So we had consistency. Now, we could add one more thing, because potential functions are not unique. You can add any number you want, but here's the thing to do. If you're looking for a potential function, choose the easy one. So what number do we add? 0! Yes! Yes! And so our final answer for finding the potential function is f of x, y, z is equal to sine y plus xy sine z plus z cubed in some order. All right, so again, how do you find it? Integrate with respect to x, your first thought. Integrate with respect to y, your second. Integrate with respect to z, your third. And then you stitch it together. Just make sure you have consistency of your variables, and there you go. Now, if you really wanted to check, you could say take the derivative with respect to x, take the derivative with respect to y, take derivative with respect to z, and everything would work out. But it doesn't say that, and so I'm going to assume we're okay to move forward to part B. Use the potential function to find the work done by f over the path x equals 1, y equals sine t, z equals cosine t. T goes from 0 to pi over 2. Now here's the great thing. That sounds like it's a lot of work. So how do you find work? Well, work is you integrate over your curve of f dot dr. Okay? Small bit of force times distance. That's the work done to do a little tiny move. Then you add up all your little tiny pieces of work. That's your total work. But when we have a potential function, there's the fundamental theorem of line integrals that says, oh, this is, for potential functions, f evaluated. You have your endpoint, and you plug it in, and you have your start point. And you plug it in, and you subtract. You take the difference. So it's the difference between what happens at the start and end for the potential. So what do we care about the curve? Do we actually need the whole curve? And the answer is no. We only need to know two things. Where did we start? And where did we end? Okay, so let's write that in. So for us, how do we find the start and the end? Well, you plug in the start is you plug in 0. And you say, okay, so at time 0, we have 1. Sine of 0 is 0. Cosine of 0 is 1. Okay, that's our start. Now, the end, you plug in pi over 2. Okay, so where are we at the end? Well, 1 is still 1. Sine of pi over 2 is 1. And cosine pi over 2 is 0. Okay, so our answer is going to be the following. We're going to take, this is f at 1, 1, 0, subtract, right, that's our end, f of 1, 0, 1. That's our start. So, the last thing for us to do is to plug in these numbers. Okay, so here, x and y are 1, z is 0. So we have sine of y, sine of 1. X times y times sine of 0. Well, that's 1 times 0. Okay, that's good. Z cubed, 0 cubed. So sine of 1, that's where we were at the end. Subtract. Okay, now we're going to plug in 1, 0, 1. So x and z are 0. So x and z are 1, y is 0. Sine of 0, 0. Okay, x is 1, y is 0. Sine of z, sine of 1. But 1 times 0 times sine of 1 is 0. Z cubed is 1 cubed. So we get 1. So we end up with an answer sine of 1 minus 1. And that is our work. Now, is it okay that work is negative? Yes, that's okay. Work can be positive or negative. In essence, there's an orientation attached to it. And so we're not going to fret about that. But once you have the potential function, really, that does all the work for you. In essence, we were doing the fundamental theorem of calculus, right? You found the antiderivative, and then you evaluate. So it's mostly a matter of knowing how to use that. All right, well, we want to make sure we finish on time, and we still have one more problem, so let's do our last problem. Number 10. Let R be the region in the xy plane described by 1 less than or equal to x squared plus y squared less than or equal to 4. So they gave us this picture here. And let C equal boundary of R be the boundary of R oriented positively. And you'll notice in one circle, which is the big circle, and let's go ahead and just mark, that's 2. We're oriented in a counterclockwise manner. Then in the inner circle, radius 1, we're oriented clockwise. Now, why that discrepancy? Well, because there's the song, to the left, when you walk the curve, keep the region to your left. Okay, what does that mean? It means that as we go along the curve, if you imagine walking, you want to keep that region to your left-hand side. And so you'll see that when we're going on the outside curve, that's correct with the orientation. On the inside curve, we have to move in the opposite way if we want to keep our region to the left. So that's the oriented positively. Now, find the integral along the curve of terrible expression, fine, and lots of stuff, terrible expression. Oh my gosh. Oh, are we going to finish on time? Yes, we will. We will finish on time. Okay, so how do we do this? Well, okay, so spoiler alert, this is Green's theorem. So Green's theorem says what? You have a region in the plane. So we're in the plane. And you have a closed curve, and that bounds the region. That's what we have. So, and it's okay to have a hole. Green's theorem works with holy regions. That's okay. So, the idea here is the following. The integral along the boundary curve, and by the way, see that little halo there? That means it's a closed integral. That's also a clue for Green's theorem. So the integral along the boundary of our region, and that's what C is, that's the boundary of our region, of m dx plus n dy is equal to the integral over our region of, take n derivative with respect to x minus m derivative with respect to y. So we're transforming an integral on the boundary to an integral on the interior. All right, now, why do that? Well, because this may have terrible things, aka terrible. But when we take the derivatives, all right, so let's go through and see what our new integral is going to become. Integral over our region, take the derivative here with respect to x. So we're going to get 4y squared minus 2. And there's no x's. Gone. Okay, that's n sub x. Minus, take the derivative with respect to y. No y's. Gone. And now here's this derivative, 4x squared is constant, and so derivative with respect to y is minus 4x squared. And so all of a sudden, this integral already feels a lot better. It becomes 4 times x squared plus y squared minus 2. Okay, but we still have to do this. And we say, hey, there's some clues on how to finish up. What are some clues? We see x squared plus y squared. We see circles. And we say, you know, between those two clues, that tells us we better think polar. So we're going to go to polar. So to finish up, switch to polar coordinates. All right, so equals integral x squared plus y squared is r squared minus 2 dA r dr d theta. Right, so that's the dA becomes r dr d theta. So this part becomes that part. Okay, now the last thing. Where does theta go from? We go all the way around. 0 to 2 pi. Okay, so that's the bounds. Where does r go from? Well, r always relates to the center. Polar coordinate says, how do I relate to the origin? You have a direction, so we start moving in a direction, and then we hit, and we keep going until we hit again. So we start when we hit the first time, which is at distance 1, stop when we hit the second time, which is at distance 2. So we're going to go 1 to 2. So this is our last integral. We're there, we're in the home stretch. Now before we integrate, multiply this r through, and so that will give us 4r cubed minus 2r dr d theta. So that's 0 to 2 pi. And then we get r to the 4th minus r squared, right? Because add 1, divide by 4, add 1, divide by 2. And we're evaluating from 1 to 2. Well, when you plug in 1, you're going to get 1 minus 1, which is 0. Nice. Plug in 2. 16, 2 to the 4th is 16, minus 4. 16 minus 4, also known as 12. All right, so we're almost there. That's 12 theta, evaluated from 0 to 2 pi. 12 times 2 pi gives us 24 pi. And we did it. We made it. With time to catch our breath, to relax, we can do these things. Now, you might be looking at the clock and thinking, we only have 75 minutes for this exam. What? You just took 75 minutes to do that. I said a lot of stuff. I was explaining a lot. We could have done this faster. But I will be honest with you. It is a challenging topic. There's a lot to know and a lot to do. Make sure you know how to use your tools. When you have a formula sheet, know it. Know it before you go to the test. Know how to look things up. Practice things. Know how to spot things. You know, if you recognize that this is Green's theorem, you'll save yourself so much time than if you just like, let me try 20 different things and wait until I find something. Practice looking at problems. Practice working through problems. You can do this. I believe in you. You are a wonderful person. And I'm thankful that you're working hard. And, you know, it's going to feel so good when you get through this and you do well. So keep it up. Keep doing the work. It's all going to pay off. Thanks for joining me. Thanks for spending time. I wish all the best for you. And hopefully, maybe, we'll get to see each other again. Okay. Bye.